This week, we'll be practicing balancing equations and finding mole ratios. Let's review. What makes a chemical equation balanced? If you're thinking about the reactants and the products and that they should be equal or something, you're on the right track. In a balanced chemical equation, the number of moles of each element in the reactants is the same as the number of moles of those exact same elements in the products. For example, we have the chemical reaction to the right. N2 plus 3H2 yields 2NH3. Let's look for the number of nitrogen and the number of hydrogen on each side of this reaction. So for the reactant side, I see the subscript 2 below this nitrogen. So that means we have 2 moles of nitrogen on the reactant side. For hydrogen, we have a subscript 2, but we also have a coefficient 3. That coefficient means that we have 3 of whatever that is. So that's H2, a diatomic molecule there. So each of those has 2. We have 3 total. That's 3 times 2 becomes 6. So we have 6 hydrogen moles on the left, on the reactant side. On the right-hand side, we have 2 moles of ammonium. So it's a different product than we started with. We want to make sure that we still have the same amount of nitrogen and hydrogen that we started with. So we look at our subscripts. We have no subscript under the nitrogen, so we can assume a 1 there. But we do have a coefficient 2 in front, and that 2 gets multiplied by both subscripts. So that 2 goes toward the 1, and we have 2 moles of nitrogen. For hydrogen, we have a subscript 3. That subscript 3 tells us that each ammonia molecule has 3 hydrogen within it. So 1 mole of ammonia would have 3 moles of hydrogen. However, the coefficient 2 also multiplies by that 3. So 2 times 3 means 6. So we have 6 hydrogen in the products and 6 hydrogen in the reactants. Those equal follows the law of conservation of mass. Nitrogen has also been conserved. We started with 2 moles of nitrogen and ended with 2 moles of nitrogen. So we did not create nitrogen or hydrogen, and we did not destroy nitrogen or hydrogen. This is a balanced chemical equation. Now I'm going to ask you to practice balancing equations, and we'll check them together. Here are some guiding steps as you start balancing equations. First, count the number of each element on each side of the reaction, like we just did in the example. Look for the arrow in the middle of the reaction to tell you the difference between your reactants on the left and your products on the right. Add whole numbers in front of your elements or compounds to match the number of elements on the other side. You might have to do this more than once, as once you change one element, this will cause a chain reaction, and you might need to then recount the elements on both sides, and then add more whole numbers in front. That's changing the coefficients. We have to use whole numbers as we're balancing chemical equations, never decimals or fractions. In this example, solid magnesium reacts with gaseous oxygen to produce magnesium oxide, written as MgO2, yielding MgO. We will now balance this equation. First, you'll want to list what you already have. So I look on my reactants, that's on the left, and I see I have 1 magnesium. I know I have 1 mole of magnesium because there is no number before or behind. So there's no coefficient and no subscript. Therefore, I can enter a 1 for both. So a 1 for the coefficient, 1 for the subscript. So I have 1 mole of magnesium. With oxygen, it also does not have a coefficient or number in front, so we're going to enter a 1 there, but it does have a subscript. That subscript 2 tells us that we have 2 moles of oxygen within 1 mole of diatomic oxygen, O2. So that means we have 2 moles of oxygen total in our reactants. For our products, we have MgO, which contains 1 oxygen and 1 magnesium. There are no coefficients in front, so we have 1 mole of that. Therefore, 1 mole of each. As you can see, oxygen on the reactants does not match with oxygen on the products. So we will need to balance this oxygen. To start balancing this equation, we'll add a coefficient, the 2, before magnesium oxide. This changes not only the number of moles of oxygen, but also the number of moles of magnesium, because the 2 is in front of the entire magnesium oxide compound. So yes, we have successfully matched our oxygen with oxygen, 2 moles of each on the reactants and products, but now our magnesium does not match. So we have 2 moles of magnesium on the products, but we only started with 1 mole of magnesium. This does not follow the law of conservation of mass, as we somehow ended up with more magnesium than we started with. We will have to go back to step 1, or we've just done step 1 and counted, and now we'll have to go back to step 2 and add another coefficient. Okay, so now we've added another coefficient in front of magnesium on the reactant side this time. So this changes the total number of magnesium on our reactants to 2 when it was previously 1. This now means that magnesium moles match across reactants to products, and we had previously matched our oxygen with our oxygen. So this now follows the law of conservation of mass and is considered a balanced chemical equation. In this next example, we will balance the equation of carbon monoxide, CO, reacting with dioxygen, O2, to produce carbon dioxide, CO2. First, we'll count the moles of each element on the products and the reactants. We'll start with carbon in the reactants. I see carbon as part of carbon monoxide, and I see that it has no coefficients nor subscripts, so there is 1 carbon in the reactants. On the products, carbon is present in carbon dioxide. There are also no coefficients or subscripts to start, so there is just 1 carbon in the products. Now we'll look at the oxygen. The oxygen is present in both the carbon monoxide and in dioxygen with itself. So there is no subscript for the first oxygen nor a coefficient, so we have just 1 within carbon monoxide, but then as part of dioxygen, it's 1 oxygen bonded with another, so we have 2 oxygen here. So that 2 plus 1 means we have 3 oxygen on the reactants. On the product side, we have oxygen present in carbon dioxide. There's no coefficient, so we know it's an imaginary 1. And then we do have a subscript. So that subscript means we have 2 moles of oxygen there. So we have 2 oxygen on the product side. So we'll look at this to see if they balance out, if they match. Carbon does match with carbon. There is 1 carbon in the reactants, 1 carbon in the products. Those are already balanced. Oxygen, though, is not. Oxygen has 3 moles of oxygen in the reactants and 2 moles of oxygen in the products. So these do not match, and somehow we lost some oxygen in the reaction, which is not possible. It does not follow the law of conservation of mass. So we'll have to start with our oxygen. Since we're not able to get rid of any oxygen, let's go ahead and add some oxygen to the product side. So we'll change the coefficient in front of carbon dioxide to a 2. This will change the number of oxygen present and the number of carbon present, because the coefficient multiplies by both subscripts. So carbon had an imaginary 1 as its subscript because it did not have a subscript. So that 2 multiplies by the 1, and we have 2 carbon moles now in our products. For oxygen, we were trying to get closer. We had been at 2 and we wanted to get closer to 3, so now we've multiplied by 2 and we now have 4 oxygen. That's because we have a 2 coefficient and a 2 subscript. The 2 will multiply by the 2 to make 4 moles of oxygen in the products. This does not match with our other side at all. In fact, you might be thinking, well, this is even worse, because not only does our oxygen not match, but our carbon also does not match because it previously matched. So neither of these match. So are we closer? Let's see. Let's try to add some more coefficients. In order to make our equation balance out, we'll need to add another coefficient. This time we wanted to add it to the reactant side because we had less oxygen and carbon on that side than we did on the products. So we'll add our 2 onto the left side in front of carbon monoxide. This 2 coefficient changes both the number of carbon and oxygen. We had no subscripts for carbon monoxide, so that means we have imaginary 1s there. So that 2 multiplies by both imaginary 1s. So we have 2 carbon on the left side with the 2 multiplying by the 1. For the oxygen, we have 2 moles of oxygen within carbon monoxide, but we also have another 2 moles of oxygen within dioxygen. So those add together to equal 4 oxygen, which are present on our reactants. So now this does actually balance out. We have 2 carbon on each side, and we have 4 oxygen on each side. So this is a balanced chemical equation and does follow the law of conservation of mass. For this last example, we'll look at a decomposition reaction. We've got potassium chlorate to start, and that decomposes or breaks down into potassium chloride and dioxygen. Let's attempt to balance this equation. First, you'll want to count the number of each element in moles on both the products and the reactants. Let's count what we have to start. I see that we have 1 potassium in the reactants and 1 potassium in the products. Those already match. I also see that we have 1 chlorine in the reactants and 1 chlorine in the products. Chemical symbol Cl. For oxygen, we have 3 moles of oxygen in the reactants, subscript 3, but in the products, the subscript changes to a 2 within dioxygen. So those do not match. Some of our oxygen appears to have disappeared, but that is not possible due to the law of conservation of mass. So we will have to add coefficients. We cannot get rid of oxygen, so we'll need to add coefficients to the product side because that's our lower amount. We have less oxygen on the right-hand side, so that's the direction that we'll have to add our coefficients first. You might notice that we had 3 oxygen in the reactants and 2 oxygen in the products, and it might be best to solve this problem by finding the lowest common multiple of 2 and 3, which happens to be 6. So if we can make there be 6 oxygen on the products and 6 oxygen on the reactants, that would be a good place to start. So we'll add a coefficient of 3 in front of the O2. This changes our total number of oxygens on the products to 6 moles of oxygen. That's because the coefficient 3 multiplies by the subscript of 2 to make 6. 6 moles of oxygen now present on our products. This does not match the moles of oxygen on the reactants, but we know we can get there because 3 and 2 are multiples or formed a multiple of 6. So the next thing that we'll do as we balance this equation is add a coefficient to the reactant side. That's because we had less oxygen on the reactant side than the product side, and so we needed to add a coefficient there to attempt to make them even to balance out. So we'll add a coefficient 2 in front of potassium chloride, and this changes the total moles of oxygen because the 2 coefficient multiplies by the 3 subscript to give us 6 moles of oxygen, which now matches with the 6 moles of oxygen we have in our products. Yay! However, in attempting to match our oxygen with the moles of oxygen on the other side, we have also changed the number of potassium and chlorine present in our reaction. That's because our 2 coefficient multiplies by both of their invisible subscripts to now mean that we have 2 potassium and 2 chlorine present in our reactants. This does not match with the potassium and chlorine on the other side. And in fact, for both of them, the other side is less than. So that's the direction that we'll have to add a coefficient. You might already see where we'll need to add it. What number will we add? Exactly. We'll add a 2 in front of potassium chloride. This will change both the number of potassium, K, and chlorine, Cl, that we have present in our products. Now, both of these also match the reactants. 2 potassium on the products matches the 2 potassium on the reactants. 2 chlorine on the products matches the chlorine on the reactants, and our oxygen previously matched. So this is now a balanced chemical equation that follows the law of conservation of mass, because we know that mass can be neither created nor destroyed. The amount of each element that we have must remain constant throughout the chemical reaction. Now that we've practiced balancing equations, let's review those steps again. First, you want to count the number of each element on each side of the reaction. Look for the arrow in the middle to separate your reactants from your products. Add whole numbers, those are your coefficients, in front of elements or compounds to match the number of elements on the other side. Finally, you might need to repeat steps 1 and 2. Count the elements again and add more coefficients until all elements match. Remember, we cannot use decimals or fractions, only whole numbers. As we've just seen, it can take quite a while to balance an equation. Once you change one coefficient, you might need to change another 1 or maybe 2, 3 more. This can cause a chain reaction. So why do we have to go through the trouble of balancing these equations in the first place? One of the laws of the universe is the idea that mass is neither created nor destroyed in a chemical reaction. We call this the law of conservation of mass, which I like to think of as the circle of life. So within the circle of life, we all are a product of everything and everyone that has come before us. And we are a reactant in everything that comes after us, exactly like in our balanced chemical equations. The law of conservation of mass is the backbone of a balanced chemical equation. But a balanced chemical equation now has become a powerful tool that you can use to solve further problems. A balanced chemical equation also becomes a key to other conversion factors that we can use, such as the mole ratio. We'll explore that more next. Now we'll look into mole ratios and how to find these from balanced chemical equations. The mole ratio is defined as a conversion factor that relates the amount of moles of two substances in a reaction. You've probably used ratios in math class. They're similar to fractions in that they're another way of representing relationships between numbers. A ratio is written with a colon between the two numbers, and the order of the numbers does matter. And this ratio is written 3:2. So we'll be using ratios within chemistry to find the relationship between two substances in a reaction. So it can be a reactant and a reactant, a product and a product, or a reactant and a product. We'll be using the mole ratio then to solve stoichiometric problems. To find the mole ratio, first look at the whole numbers in front of each compound in the formula. These are called your coefficients. If there is no number in front, assume an invisible 1, such as in the case of N2. Then you'll want to write your ratio as two whole numbers with a colon between them. For example, if we were trying to find the mole ratio between N2 and H2, we would write that as 1:3 because we have coefficient of 1 in front of the N2 and a coefficient of 3 in front of the H2. Notice we do nothing with the subscripts. The subscripts are not important for a mole ratio. The mole ratio tells only the ratio of the coefficients between those reactants or products within a chemical equation. As you're writing your mole ratio, pay close attention to the order of your numbers. Which one needs to go first as you're solving stoichiometric problems? In our first example, we'll find the mole ratio of potassium chlorate to dioxygen. So we'll notice the order that it's asked in, and we'll find those in our balanced chemical equation. Recall that we balanced this specific equation earlier in the lesson. We'll write our mole ratio like this, 2 with a colon 3, to indicate that we have 2 moles of potassium chlorate that would produce 3 moles of dioxygen. We can use this to solve stoichiometric problems further along. In this next example, we'll look at the same chemical reaction, but find the mole ratio between potassium chlorate and potassium chloride. We find potassium chlorate in the equation, and we find potassium chloride. We notice the coefficients. Those are the numbers in front. In this situation, they're the same. They're both 2. So you could write this mole ratio as 2 to 2, or you could reduce it, just like you can reduce a fraction. So you could rewrite it actually as a 1 to 1 ratio. Either I would accept. Either can be used actually to do a stoichiometric problem as well. Now we'll look at a different equation. We balanced this one earlier today too. We have 2 moles of carbon monoxide that reacts with 1 mole of dioxygen to produce 2 moles of carbon dioxide. What is the mole ratio of carbon monoxide to dioxygen? If you said a ratio of 2 to 1, you are correct. There are 2 moles of carbon monoxide present in this equation, and that it reacts with 1 mole of dioxide to produce 2 moles of carbon dioxide. Therefore, the numbers that we need are the coefficients in front of carbon monoxide, the 2, and the invisible 1 in front of the dioxide. That becomes a ratio of 2 to 1. We can find other mole ratios within this equation though. So now let's look at the mole ratio of dioxide to carbon dioxide. So O2 to CO2. So we'll look at our balanced chemical equation, and anytime we don't have a number in front, remember there's an invisible 1. Using the coefficients in front of the O2 and the CO2, we can then create a mole ratio. That mole ratio becomes 1 to 2, written as 1:2. This ratio will be used in stoichiometric problems moving forward. As you practice the homework to balance equations and find mole ratio, consider this question. Why do you think chemists use a mole ratio in the first place, rather than a mass ratio? All right, thanks for watching.